Okay, today we're going to learn about finding volumes of irregularly shaped objects using a process called using cross sections. And so before we do this, let's remember how we found volume of 3D objects in earlier classes. The basic formula for any type of volume is take the area of the base times the height of the object. For example, let's say we had a cylinder. Our area of our base is the circle. And so we took the area of our base, the area of a circle is pi r squared, and we times it by the height of the object. Okay, how many of those infinitely circles that we stacked upon each other to form the cylinder. So that's how we got the volume of the cylinder is pi r squared h. Okay, we're going to use a similar process, but what's different now is that the circle is not going to be the same size. It's going to get smaller or larger as it goes along the shape of the object. So as you can see down here in the bottom in picture A and B, and looking at B here, our cross section is this rectangle. But the rectangle, when it gets close to the x-axis, is much larger than the rectangle as it gets close to D, it gets smaller. But we still do the same thing. We find the area of that cross section. So we use our formula for the area of the base of that cross section, which would be in a form of variables because the width and height will change, but we're still going to use that length times width formula. And then we're going to times it by how thick that individual cross section is. Well, with calculus, we're going to do these infinitely small thickness, infinitely thin. And so our height of this rectangle is simply going to be dx or dy. In this case, the drawing of B, it's dy, and the drawing of A, our height is dx, infinitely small x. Now, then we're going to do infinitely many of these cross sections in the shape of that object. And so that's when we involve integrals. So to find, using our calculus notation, if I'm looking at figure A here, might want to integrate this rectangle from A to B on that x-axis of the area of the base, which I'm going to call A of x, times the thickness of each individual cross-section, which is dx. And so our formula for finding area volume using cross-section is to integrate from A to B of the area of the base times the height or thickness of the cross-section. Now, I went ahead and drew the picture here. You won't always have the picture. So we want to find the volume of a right pyramid with a square base of A and altitude of h. So I chose to turn my pyramid on its side so that the vertex of the pyramid is at the origin and the center or the altitude of the perimeter is on the x-axis. I just did this so it's easier to work at. So I can say that the height of my altitude there, the height of my triangle is h. So I label that as the distance h on the x-axis. Now here's my cross section, which is a square base, so it's a square. So I know that it has a square base of side A. Okay, and then I chose my A to be the height of my y. And so that gives me 2y, because remember, A is the full height, and I took the center of my triangle is in the middle, so I needed to double that. So my area of my base in this case is the length of the side squared, or 2y quantity squared, or 4y squared. Now I need to get this y in terms of x. So I look at my second just 2D object here, and I'm going to use something called similar triangles to relate my x to the y. So this helps you kind of see why that distance was 1/2 a, not just a. All right, so I'm going to looking at this small triangle here that has I'm going to say that the distance x is 2y, or let's do y to x, is equal to, and then looking at this larger triangle, corresponding size, that'd be 1/2 a, is my height of that triangle, and its base is h, length of h. Okay, I'm going to get this, and I'm going to solve this equation for y by multiplying each side by x and simplifying the compound fraction. You end up with y is equal to ax over 2h. Or I could also say that my area of my base, replacing that y with ax over 2h in quantity squared, Okay, squaring each side, that's a 4 on top and 4 on bottom, simplified out, so it leaves me with an a squared on bottom, and I'm going to write the x squared out to the side. Now, the reason why I put the x squared out to the side is a squared and b squared are not my variables of interest, so they are considered constants. The square base of a and altitude of h. Those are given values. We just don't know what the values are. So x is my variable. And so I write this as a constant times x squared, so it's easier to integrate when I get to it. So now I'm going to set up my formula for the volume. Remember, that's the integral from a to b, so I started at 0 and I went to h on the x-axis. That's what I'm integrating. Area of the base and times our thickness, which is dx. So 0 to h, area of my base we figured out to be a squared over h squared times x squared dx. So a squared, h squared is a constant, so I can just bring that constant out, and then I can just integrate from 0 to h of x squared. We know the integral of x squared is x cubed over 3. And now I'm going to replace every x with h minus every x with 0. And we know that that just easily simplifies out to just h cubed over 3 minus 0, so I don't have to write that 0. My h cubes and my h squares simplify down. And so I left with 1/3 a squared h is our formula for the volume of that pyramid, and that should be familiar to you. A curved wedge is cut from a circular cylinder of radius 3 by 2 planes. One plane is perpendicular to the axis of the cylinder. The second plane crosses the first cylinder at a 45-degree angle to the center of the cylinder. Find the volume of the wedge. So here's kind of how, again, you probably will not have this picture. Sometimes you will, sometimes you won't. But this is the translation of that picture. And we notice that that wedge is crossing that cylinder at 45 degrees. So there's my 45-degree triangle in the center of that wedge. Notice I purposely put the center on the x-axis and the y-axis there, so I can I want to pick the numbers, variables easy to work with. And since that's a 45, 90 right triangle, I know my two sides are the same. So if I make that distance x, the height is also x of this right triangle. So then that would let me figure out, and I know I have a cylinder whose radius is 3. So using right triangle trig and stuff like that, I can figure out that I have one half of that rectangle is square root of 9 minus x squared. And then I just simply double that for the two sides. So I get the length of one of those sides of the rectangle, and I got that point on the axis. So now I can figure out the area of my cross section, which is that red rectangle. And to find that, we take our length times our width. And then simplifying that down, it's just going to be 2x, the square root of 9 minus x squared. Now remember, to find the volume, we're going to integrate this cross section here from A to B. So I start, on that x-axis, my smallest x value is 0, my largest is 3. Again, I knew that because my radius of my cylinder is 3. So volume is going to be the integral from 0 to 3 of the area of the base, which we just figured out to be 2x, the square root of 9 minus x squared, times our thickness of our rectangle, our cross section, which is dx. Now, this one's kind of, we can't integrate products, remember? We're going to learn some techniques later in this year to figure out some ways. But the only technique we really know how to do is the u substitution. So I'm going to do u sub here, making my u 9 minus x squared and my dx du divided by -2. Now remember, I need to change my upper and lower bounds of my limits of integration. So my new lower bound is 9, my new upper bound is 0. Okay, and then I'm going to replace my u, and I'm going to rewrite the square root as u to 1/2 and the du over 2x. Now notice the two x's cancel each other out, and I'm left with just negative the integral from 9 to 0 of u to the 1/2 du. Remember, we cannot integrate when our upper bound is smaller than our lower bound, so we flip that over and negate it. So I end up with the integral from 0 to 9 of u to the 1/2 du. And then this is just simple to integrate. And I get 2/3 u to the 3/2. And that's going to be integrated from 0 to 9. So first thing I'm going to do is I'm going to replace the u with 9. So 9 to the 3/2 gives me 27, and replacing it with 0 gives me a 0. And so I get 2/3 of 27, which is 18. So my volume of this object, 3D object, is 18 cubic units. Okay, that is how you find volume using cross-section.